We're ready? Good?
Yep.
All right. Good afternoon. My name is Carlos Munoz, and we are the NJIT RockSat team. And this is our critical design review. Start up here.
I'm Nathaniel Gunwan. I'm the electrical design lead.
My name is Lucas Stulik.
I'm Ali Rahimi.
I'm Daryl Torres. I'm the project manager.
And Aziz, if you want to introduce yourself real quick.
I'm Aziz. I'm the AI and CS lead.
All right. We can go straight into the PDR action items. So we included our updated frequencies for user guide compliance for the Rock Iridium constellation radio frequency. We also added labels and pictures for our arrow design, key dimensions that were needed, as well as expected hardware components and all that stuff for the electrical section of our payload. And of course, we looked for a way to introduce Nebraska's Big Red Sat onto our deck. The mission statement hasn't changed from the PDR, but I'll do a quick summary of it and then we'll skip through the rest. Mission statement, the Arrow mission statement, our NJIT mission is to design and demonstrate a dual-stage sub-orbital platform Arrow, which utilizes the stationary payload Overwatch as a central hub to deploy Scout. Together, these systems will characterize the ionosphere by measuring electron density and analyzing the dynamic forces experienced during reentry. All right.
So the Y space, that still hasn't changed from the PDR. The mission's still the same. Scout's going to be launched out of the rocket, collecting the electron mass density using the Lagomir probe that we're making ourselves. And using that data, we can use it for future RockSat missions. And for this, that data will also support the research at the Center of Solar Terrestrial Research.
So mission objective 1, same from PDR. We just want successful deployment and stabilize Scout during its reentry mission. And yeah, continue on.
All right, got mission objective 2 is the Lagomir probe and the data collection. This is not changed from the CDR, so I'm not going to go through it, but it's going to measure electron density, thermodynamic properties, and dynamic forces throughout reentry. That's the whole purpose of the mission.
Objective 3, also unchanged from PDR, just establishing a reliable long-range RF module and being able to get that data back and analyze it in post-mission.
As for our mission objective, the mechanical breakout, we do have a few changes within our Overwatch payload with new and improved locking mechanisms for the plate itself. Make sure that the payload is more rigid and able to withstand the 20 G's thrust in both lateral loads, and the factor safety of 2.0 is what we're looking for. We'll talk about this more in detail throughout the presentation.
This is our electrical objective. There's only 3 categories of power and protection. We will regulate 28 volts to clean 3.3 volts or 5 volts. There's the data acquisition for the Overwatch and the Scout. So we'll be sampling the electron density and plasma data using a Lagomir probe, and the signal integrity. So we just want to establish a strong and stable connection with all the components.
Moving on to the software objectives, nothing much has changed from the PDR. Obviously, both Scout and Overwatch will have their own proprietary flight software. We'll be collecting and transmitting data. We're still using Arduino systems. We'll be using C++ or C softwares, maybe a little bit of Python. That's a little update from our end. We are doing a little bit of flowcharts for the pseudocode itself for the event sequence. That's been started from our end so that we can work with the electrical team so that everything's working fine. We are still not doing any kind of AI on board, but we will have post-mission for an analysis, we'll have AI.
All right, and we're on the timer event matrix. It did not change as much. So we have the beginning at T-60 and to T plus 332. That'll just give power to the entire mission, the Overwatch aspect of the mission. And then we'll use time event 1 also to launch out Scout from the rocket. And then we'll use time event 2 to start the data logging for Overwatch so we can start that the radio transmission. And when we were talking with Nebraska, we thought that we could possibly share some of these time events and also maybe get rid of time event 2 and only have time event 1 if necessary. So
For the concept of operations, also all remains the same. At T plus 165, Overwatch data starts logging. T plus 160, Scout is ejected, and final data dump is at T plus 320 seconds. This one.
So as for expected results, we are expected to receive Langmuir-Probe raw data between current and voltage to create a curve for a segment of the flight. We're using acceleration versus time graphs, IMU, raw data using acceleration, magnetic fields, and extracting these data points and creating graphs out of them. That's, of course, the humidity sensor versus time as well. So the graph on the bottom right actually comes from the RockOn experiment. This is the data that Darren and I collected during the RockOn mission this past year. And then on the left is just a research paper that had Langmuir-Probe data points and the current versus voltage graph. Next slide. And then this is all the breakouts that we did for the RockOn mission. So we are expecting something similar to this for our mission as well. Humidity, acceleration, IMU, the gyro, all that stuff we're expected to receive during our Arrow mission.
For the comprehensive success, it's been updated. The top 4 points are the same. The only thing that's changed is to include Big Red Sat-1 from Nebraska. Essentially, we just talk about how the Scout must deploy and operate without interfering mechanically, electrically, or thermally with the Nebraska's team experiment, and ensuring that we can reliably send Scout out without any interference. Minimum success, again, is all the same aside from that we're integrating Nebraska, and we would consider minimum success whatever they would consider minimum success, meaning that our module has not affected theirs.
All right, and then we move on to the sister overview. For Overwatch, the top level requirements are pretty much the same from the PDR, is to receive data, data storage, and data retrieval. And then the Scout top level requirements is to launch out, obviously, collect the data and transmit the data and make sure that all the sensors are housed properly for launch.
So for the design overview of the whole Aero project, some changes from our PDR. As you can see, that I will dissect it a bit more on the next slide. We did decide to, instead of having a custom electrical box, we're going to outsource it. It's just easier for dimensions. Obviously, now integrating, which we chose option 2 as the best way to integrate with Big Red, is to have their project on top of ours, above our electrical box, and having the shelf. Also, a bit of a minor thing, we did push back the spring-loaded system, as you can see. And going on to the next slide, we're going to dissect it a little bit more. The deployment system itself, we did put the locking tabs. That was something that wasn't there before. The shelf, and then going on to the next slide, because I want to show the mil-spec connectors. So that was something that we made. That was a big decision from us. That's why we wanted to outsource the box specifically, because before we had the connectors running from the top, and if that wouldn't be possible with integrating with Nebraska's Big Red project. So we decided to use these mil-spec connectors that lock into place and water won't get through them. So that's a big plus on our side, and also the big vibrations and all of that really mess up our connectors. So the mil-spec was the best way to go with this one. And yeah. So the design changes with Big Red, like I said, we'll be having their shelf integrated with us. Obviously, we're going to be pushing our Scout a bit farther out from the zone before. Obviously, we did get permission from that. That way, our project doesn't interfere with their project doesn't interfere with our project. That's why we like the option shoot the best, because it's our electrical box. It's not something that's moving or anything like that. It's going to be stationary, and it won't mess with them.
Moving on, for the software overview, it's going to stay pretty much the same. Overwatch software handles the deployment, the RF link, etc. Scout still always obviously has all the sensors, and we're going to be sending data and having the redundancy. We're going to have the live data. And then obviously, like mentioned earlier from the updates, we're testing out, we do a pseudocode flow for the Arduino time testing. And for the Langmuir Pro processing program, we're trying to use the old RockSat data to test out this program and the pseudocode so that we can get the most amount of accuracy for the conclusions we will pull out later on.
All right, and now we move on to the model drawings, which is required for the CDR, and also required for us when we got funding from our institute. They wanted all of these drawings. So here's the overall view drawing. This is all the item numbers we have. I mean, all the items that we have that are going to be on this SolidWorks model, including Scout, Overwatch, the electrical box, and the Big Red project. This is more model drawings from Scout. We have an overall diameter of 4.75. We gave a little bit of wiggle room because I know the top of the deck is, the max we can go high is 5.13 inches. Then the overall length of Scout is 7.96. None of this changed from the PDR, but we know that you guys wanted the dimensions for this. And then inside of the Scout is the electronics cage that hold all the electronics inside there. And then towards the rear is the Langmuir probe and the antennas that are going to go out. Then we can move on to Overwatch. We got a little closer up view of the actual ring system with the gears. So basically there's just a stepper motor here that'll spin this ring and that'll release these tabs that are holding on Overwatch. That are holding on to Scout. And then towards the bottom, it's not shown here, but there's a little locking tab so that this ring does not spin due to any vibrations from the rocket. And then the overall height for all this is 5.1 inches. If it's too close, we can always like shave off a little bit off the top, but it shouldn't be an issue. And then, yeah, this is the electronics box is 7.5 inches and 4 inches. That did change from last time. We went a little bit bigger just so we can have, we went a little bit wider because we couldn't go taller because of Nebraska. And then right here, this is the locking mechanism, the thing that holds the locking mechanism together. This is just more part drawings that we're required to have. And then this electrical box, this is the integration of the mil-spec connectors. We will be buying this box from McMaster-Carr, but we will be adding these holes into it so we can add the mil-spec connectors.
Moving into the system level architecture, we have split the electrical design into two distinct assemblies, the stationary Overwatch mainboard and the deployable Scout stack.
For the subsystem overview, same as PDR, but we have some changes that Nate will go over with the electronics. The Overwatch subsystem feature functions as the mission's command center. It integrates the flight computer and safety relays to drive the SPN probe and manage the Scout separation. It provides the necessary mechanical and electrical interfaces to ensure the safe transport and time release of the deployable payload. Features custom-built deployable system, data collection, transmission modules, and custom PCB board, which is now split into two, which they will go over.
So this is the topology of the Overwatch mainboard, which acts as the mission hub. As you can see from the top and follow down, we have the power entry. The power enters via the TA15 connector and immediately passes through our protection block. We split the power into two isolated domains, a 5-volt high current rail for the motor and the Arduino, and a clean 3.3-volt rail for the sensitive RF and sensors. There's a safety logic. We use optocouplers to physically isolate the NASA timer event lines from our logic, ensuring that the high voltage spikes cannot damage the flight computer. And for the control, we have the Arduino Uno R4, which manages the state machine, triggering the stepper driver to deploy the Scout only when the safe launch conditions are met.
For the subsystem overview of Scout, Scout integrates various subsystems and sensors to manage power distribution and capture electron density and flight dynamics. It still features Langmuir probe, data collection, and transmission modules, and our custom PCB board, which is now split into two for a safer experiment.
This Scout payload is electrically self-sufficient once deployed. It runs on an independent 7.4-volt LiPo battery, regulated down to operational voltages. The comms redundancy, we have a primary rock block 9603 modem to transmit coordinates and data via the Iridium satellite network. As a backup, an onboard XP Pro transmits telemetry back to the Overwatch. For the science block, the bottom block, it represents the science module, which generates the high voltage to drive the Langmuir probe.
For the Langmuir probe, it also remains the same. Langmuir probe system resides within the Scout payload at the rear. It is fully custom built, and we now have our own testing lab where we will begin experimenting with which material we want to use. Our plan is still, we have three options. two being stainless steel, one iridium coated, one gold, or simply a tungsten rod. For the housing, we are still split between PETG or 6A or PA612, both ESD safe, 3D printed, or by using that polymerization, printing it in ceramic, which would give us a higher resolution. Custom built PCB board will control this, and amplifier will increase voltage from 3.5 volts to 50 for the sweep.
Zooming in on the science module, this is the heart of the experiment. To measure the electron density, we need to bias the probe. So we use a specialized HV DC to DC converter to step the battery voltage up to a range of 50 to 100 volts. The resulting plasma current is extremely small, so it is passed through a precision op-amp sensing circuit and then isolated before being read by the flight computer. This isolation is critical to prevent the high voltage bias from frying the logic lines.
So this is an exploded view of our Langmuir probe model. At the far left, you have the RF antenna, which will send data back to the Overwatch. And in the middle, you see the rods, which we are debating on which material and coating to use.
This is the finalized schematic for the Overwatch mainboard. We adopted a motherboard architecture where the Arduino and breakout modules plug into headers on the custom board. This modular approach allows for rapid repairs. So the key figures include the input protection, the polyfuses and TVS diodes at the DA15 entry, which are at the bottom left, the signal isolation, the optocoupler array separating the 28-volt rocket signals from the 5-volt logic, and stability. We have placed decoupling capacitors at every active component to filter noise, and a bulk capacitor at the motor driver to handle inductive load spikes. So this is the electrical components or the bill of materials for it. We selected the Arduino R4 Wi-Fi as the main controller because it offers the speed of a 32-bit processor while maintaining the electrical robustness of 5-volt logic. For power, we are using the Pololu switching regulators for their high efficiency, ensuring we don't waste battery power as heat inside the canister. These are the component images. Here you can see the physical hardware. The use of breakout boards like the Adafruit ISM330 and Pololu regulators allows us to easily replace the individual components during testing without scrapping the entire PCB. This is the electrical components for the Scout. For the Scout, space is the primary constraint, so we selected the Arduino Nano 33 IoT for its small form factor and integrated IMU. For the critical satellite link, we are using the RockBlock 9603, which is the industry standard for reliable low Earth orbit communication. These are the component images. The XP power high voltage module seen here is potted and shielded, so it's essential for preventing arcing in low pressure environment of the upper atmosphere.
So we're moving on to the user guide compliance. We are, I would say, 75% sure that we're within the center of gravity for our actual payload with Nebraska integrated as well. We are waiting for final CAD models from Nebraska to finalize that actual center of gravity. And for the RF links, we are using two different RF links. So now we've updated it from the PDR, including the RockBlock radio frequency as well. So the minimum is 1 watt to 2 watts max, with an average of 1.6 watts and 1,621 megahertz. Everything else has not changed from the PDR. So yeah.
So the special requests, this is with the integration with Big Red. This design here solidifies our integration with Big Red. I mean, if things do change, we do have some wiggle room to work things out. The only special things were for us specifically was having the Scout have the keep out reach zone, so it'll be closer to the deck a little bit. Obviously, that was permission that was granted. And just having the Big Red's project on top of our electric box. And yeah.
The weight budget had a slight change in weight due to the fact that now we're no longer creating the electrical box itself. We are actually outsourcing the box, which is lighter in our case. And we are still waiting for a confirmed Big Red payload weight. But as of right now, we are still using their 0.24 of a pound from their PDR. Same thing goes for the budget power. Nothing has changed. Everything has stayed the same. We're still waiting for confirmed numbers from Nebraska to finalize our power budget. But as of right now, we're still continuing to have the battery use amp hours of 0.251.
All right, and this is the power budget you guys wanted us to show you. Let me see, just showing that we're using GSE 1 and 2 and time event 1 and 2. And yeah, we're still waiting on confirmation from Nebraska what are they going to use, but this is what we have so far. As for the pin assignments, this is what we have so far. This is from GSE 1. We'll be using time event. This is redundant.
Just T1, T2.
T1, T1.
It's the same.
The same. Yeah, it's the same as before, but now in the Excel file that you wanted. And then for the power IDC, we're just supposed to sign this, I believe. So we signed it, put our name on it. I don't think we're supposed to make any changes to this.
It was also the same, just in the deliverable format now.
Yeah.
GSE 1 time on T minus 60, GSE 2 time on at T minus 45 to power the Overwatch system, T1 and T2 to deploy system and final data log. So the timeline, you can look in the middle. That's the CDR. That's what we've accomplished so far. Below that is the STR. By January 5th, we hope to have a fully assembled payload prototype. By the 15th of January, conducting bench tests for power, sensor output, and data logging. By the end of the month, begin vibration and thermal testing. And hopefully that would give us enough time. These are obviously slightly ambitious, but we have over 2 weeks of wiggle room at the end there to finalize anything before the STR, as well as the first payment, the 16th of February. So prototyping and analysis. So far, Daryl has the 3D printed prototype we can show you, especially at the end of the presentation. We have 3D printed Scout, so the Scout electrical cage, which resides inside Scout. Functional Overwatch locking mechanism with stepper motor, and the Overwatch electrical housing. I don't think we have that here. So this was mainly done to analyze how everything's going to fit together, give us final dimensions of the PCB board, because we have to ensure that everything's going to fit. We also analyzed how the locking mechanism is going to function and how possible vibrations could compromise it. And one of the solutions we could go with is vertically mounting the stepper motor and using a worm gear, which would not allow backdrive and possibly make it safer. So it's just a couple of the things that we've taken away from going with another 3D model.
And these are just some of the pictures of the actual design. We have the physical ones right here. Nothing much has really changed from the PDR for Scout and specifically for Scout. The cam system, there were some minor tweaks to it. As you can see from the far right, that's the shelf that we'll be putting our PCB boards and our electronics in. Yeah.
As for our testing plan, it really didn't change much for the Langmuir probe. We're still comparing 3 different Langmuir probe coatings. So regular stainless steel with iridium coating, stainless steel with gold plating, or just a traditional tungsten wire to understand which material will provide a more accurate reading during reentry. We're still reaching out to Princeton University to arrange Langmuir probe validation in a vacuum environment. We are still testing insulation material in-house to figure out which is better for our experiment. Of course, we're doing electronic testing with the Arduino and the compatibility with our custom PCB boards, and provide a voltage sweep across the Langmuir probe and store data and send all data successfully. The software testing will be conducted as well throughout the mission once we receive all electronics and we start integrating them together. You can move on to that. As for the overall testing plan, we want to perform 50 plus ground testing deployments. We want to make sure that our Scout is working optimally once we're on the sounding rocket. Of course, we want to do electronic testing, software testing, and of course vacuum setting testing as well. For Scout, the stress test, making sure that the actual housing will not fail during reentry, make sure that the in-house electrical cage can withstand the vibration during reentry and during the ascent during launch. And of course, the thermal testing throughout the entire project as well.
So for our own Big Red Sat 1 testing plan, this basically mentions everything previously mentioned, but essentially how it would function when you have both payloads on board, that one is not interrupting the other, that there's no interference to collected data. Depending on how sensitive their PCB boards are, we want to ensure that our deployment does not interfere with their experiments and vice versa. This is the PDR risk assessment. Most of it was still in the yellow. If you go on to the next one, we can show some of the risks that we've worked on mitigating. The locking mechanism, we've analyzed how we can improve that using either a pin, a linear actuated pin to stop the cam from turning unwantedly, or using a worm gear to reduce the risk of backdraft. Then also for risk number 4, Scout and Overwatch ground out, we have a couple more ways that we can mitigate. We've talked about formal coding and using eFuses, but also using ESD safe 3D printed parts for the electronics gauge, and possibly using potting composite to encapsulate any delicate components. For risk 5, the Lagrange probe measurement failure, Nate went into this earlier, but essentially we're planning on using 2 PCB boards, which would make it safer to not allow high voltage to damage any sensitive components. And now we have the updated risk assessment for the CDR, and as we see, we're working towards making everything green.
All right, and then now we got the budget update. So now we are fully funded officially, now that we made it past the final down select. Our total cost for the whole RockSat program has not changed, but we did get the $9 grand from the New Jersey Space Grant Consortium, and then we got 30 grand from our college to do this. So now we have total funding of 39,000. We still have a pretty big wiggle room of $3,000 that could either be used for next year's projects if we decide to do it next year, or any like shirts or team bonding.
Oh, we're also sponsored. To be determined.
What?
To be determined.
Oh, and then yes, for in terms of sponsorship between any companies, we are still working that out. So there may be updates by next review. As for the project management, it hasn't really changed all that much between all the team leads. We have Yeoman, which is here with us, 2 other advisors, me and Carlos, Ali, and Luca. And then we have a couple bit more of electronics EEs that are helping us with this project, because that's where we were kind of lacking before. And as for project management, this is the full list. It's a bit longer than what we had previously. Now we have a addition of 6 physics students that are going to help us with the actual Langmuir probe. So with them, we can all really work this whole experiment out pretty well. And then this is team pictures. They're the same from last time. And then for student mentor work plan between the PDR, CDR, and STR, it hasn't really changed all that much. We have weekly meetings on Wednesdays, bi-weekly check-ins with Dr. Kim. We have a shared drive, communication platform. We have a pretty big Discord going now between all of our students, all of the team leads, and Nebraska is also included in that Discord for any updates. That's pretty much it for that. And then,
yeah, as for the student mentor plan, well, of course, we're in the CDR right now. We completed and finalized our CAD drawings. And so we're going to start proceeding over and to start manufacturing our parts once we get a green light from our college as well. And we will fully have a payload prototype, conduct bench tests for power, sensor output, and data login. We will begin vibration environmental testing hopefully with Princeton University in a thermal setting, and of course thermal testing as well. All document tested procedures will result for submissions. As for our next steps, potential failure points is manufacturing lead times. We are uncertain on the lead times of certain parts. We will get back to that once we come back from break. The difficulty of getting permission to manufacture certain parts using in-house machinery, we have to get a clear go green light with our school to use the makerspace, and of course outsourcing lead times for our PCB boards and components. we do have a few questions. Which parts of our report which parts of our reports going forward do we need to include for Nebraska in? Are we sharing pins? And who is responsible for building the shelf that RockSat, Big Red Sat sits on, essentially?
Yeah.
And that's pretty much the
And then
entire
that's the
presentation.
Awesome. Great work. We'll start with these questions here, but yeah, no, just overall, great work on all the prototyping. Again, kudos for one, making down select, so actually being manifested, but two, helping another team fly as well by so graciously figuring out the space that you had available was able to be used for them. But yeah, no, I can definitely answer a few of these questions. So the parts that of the report, just remember that you're two separate teams, even though you're sharing the same space. We are still delineating your team from their team, even in these reviews. So essentially, you really just want to worry about your institute, and then Nebraska will worry about theirs, and then our job is to help merge the two together. So what you've presented so far as the plate that they sit on, that plate they will be manufacturing, but you're essentially telling them, hey, we have this room available, and then they go, hey, we can fit on that, and then my job is to facilitate that coordination between the two until we get a little bit later down the road. But I do want to emphasize that you're your own team. So your report is only your report. You can mention Nebraska in the report if you want, but you don't have to, include any science or any results as far as that goes, or certainly not any collaboration as far as getting any, I guess, input from Nebraska. It's going to be your report in the end. And then as far as the pins, it really depends. We do have a limited amount of the lines that are available. I do have a comment about just a couple of your GSE lines a little later. But any lines that we can share between teams, including Nebraska, we will evaluate and make that decision a little bit later down the road. But since you and Nebraska are on the same plate, it makes a lot of sense to be able to share a lot of those pins, which means a lot of timing would have to line up if possible. But if not possible, then we would have to figure out a different route to go. Hopefully that answers that question.
Yeah.
Okay. And then yeah, I think I mentioned this, but yeah, the shelf that the Big Red Sat is sitting on, and even the hardware that's underneath it, I think there were a couple standoff posts or whatnot, is essentially covered by Nebraska. So they'll be in charge of manufacturing that plate to the specs that'll fit on the model, which it looks like you already have a great CAD model put together there. But any of the hardware that is required for them to interface to the deck will be Nebraska's responsibility to manufacture and then supply and cover, if that makes sense.
Yeah, that makes sense. Okay, perfect.
Awesome. Cool. Yeah, no, overall, great work. A lot of prototyping. I love to see all those parts coming together and a lot of the thinking. I did see that you're still mulling around the idea of a worm gear to help keep that cam deployment mechanism kind of in check. So that way it's not going to accidentally vibrate loose during vibe testing. I don't know how far you were able to get specifically on if that's in the design now. I guess.
It's not in the design yet, but we were discussing with a professor over the possibility of it, and we're just trying to work out how much space we can, utilize towards that, because it is a little bit tight.
Is it tight in the z-axis or a little to the side?
It's very. I mean, our whole project is now off to the side, so could pose an issue. But we do believe that would be a better way to go if we can match.
All right.
You want to show the model on the CAD?
Yeah, I can show it. Yeah. Yeah, right here. So yeah, it was a bit a little bit undecided if maybe we should move these gears to the other side, or maybe place the motor horizontally and horizontally going this way instead of coming out towards it, or facing upwards in the z-axis. That might be also another direction we can go in.
Right, I can definitely see the space constraint there.
Yeah.
I'm not sure there's another model here. I think it was a little bit before this. It was a good top-down view. Oh yeah, it's on page 24 is a pretty good model, or slide 24.
Yeah,
Yeah.
right here.
Yeah, so that's a pretty good indication. That's not a lot of space on that side. Especially it's kind of, even if you were to pivot a little bit further back, yeah, I can definitely see the challenge there. Even if it was
Yeah.
on top. Okay. Yeah, no, but the sooner you can get that, as far as how you're going to lock that down solidified, the better. That way you're not rushing to catch up going into STR, going forward. But I think you're on a solid path with your resources at your institute. And I do commend you for looking into that possibility of that ring rotating. To think in this design, it's a pretty good chance, since that stepper motor won't be powered, it might have enough to just vibrate through and then accidentally deploy you inside of the skirt. Anyway, long-winded answer from me, but I guess question, but great that you're already looking into that. All right. Let's see here. I did want to, we're kind of close to it, but just your GSE lines. We can look at it on either slide 11 or 49. One of them, it looks like you're trying to charge Scout on the vehicle, which is called out in the user guide. You are not allowed to charge at wallops, and that includes anywhere on the pad. So you won't be able to charge Scout, is what I'm getting at here. Especially from a TE line, you'll have to ensure that Scout remains fully charged until you essentially release it, if that makes sense.
Yeah, we were looking at that in the user guide. We saw that if we needed to have a charger, we'd have to specify what charger we need to use and make outputs, I believe. We were just saying this because it's gonna be there for about a couple of weeks, and we didn't want the battery to lose a lot of charge. But as we were later doing some more research, we found that the loss in battery power is pretty negligible for the amount of time that needs to be on. So we'll fix that for the next presentation.
Yeah, definitely. It's great that you're thinking about that for sure, to see how long Scout will survive being stored, essentially. Historically, RockSat experiments that do have deployables with batteries on board, especially using lithium batteries, everything's inhibited. They store for months. So they would integrate and test in June, and then they'd be able to launch in August quite easily. Not saying it's not going to be a challenge, but it's definitely something you'll need to test and fully understand how long you will last. But I'm pretty confident, the month after integration, you would have, roughly the same amount of charge in that battery if you're, electrically isolated.
Yeah, that's what
Um,
we seen. Okay.
yeah, so definitely for this one, we want to remove all references to charging then. You can charge at wallops, absolutely, after a test. If you do tie, let's say, booting Scouts to a GSE line, just keep in mind we toggle those GSE lines a lot during testing, not necessarily the TE lines. So that could potentially mean we're turning Scout on and off. So perhaps you would want to, time that to your TE1 line, which maybe you have already, that TE1 controls deploying Scout and also activating it, releasing the inhibit, so to speak. But the GSE lines will be turned on and off a lot. So that may play into how much battery power is drained during that testing sequence. But as far as charging, there is limited time to charge. You would not use the GSE lines to do so. You would have either built into the pogo pins on the back, a harness that you can easily access externally while you're integrated on the stack, that you could just plug in, or maybe even just test your battery voltage, if that makes sense. Essentially check to make sure that Scout has a full battery. That way you're not left guessing. But you wouldn't do that through any of the GSE or TE lines.
Okay, we understand. All right.
Awesome. All right. And then I think I glossed over this, but yeah, no, that plate that you've modeled already for the big red sat and shelf, if you have a model of that handy, I can definitely hand that off to the Nebraska team to see if they are happy with that design as well. I think it looks great. I think this is an excellent way to mount them. They're very short, so there's not a lot of room that they take up. But yeah, if you want to go ahead and email that model to us, that would be awesome. And then I can get any feedback from them during their review next week for sure.
Okay, we can do that. Yeah.
Awesome. And then
You want to isolate the deck and their plate, so it's not like a huge SolidWorks file.
oh yeah, you can isolate just the parts. So I think just that plate, and then probably the 4 or 5 posts that are there.
Okay.
But yeah, at a very minimum, just that plate.
Okay.
Would be excellent. And then once again, I do want to commend your team on, just modeling them in for sure. That's awesome. All right, and then a couple questions to Scout specifically. Do you know the weight of Scout as of now?
I believe it's around 7 pounds, right, or less than 7?
It's less.
5? Should be in the
Budget weight overall Scout. The body was 2 pounds. Electronic, the top, so about a little bit under 4 pounds.
Okay, so you're about 4 pounds. Just making notes here. And then you didn't request a faster deployment speed. We can definitely do that. We just need to know what deployment speed you're aiming for and what you're actually be deploying at. So whether that's 1 inch per second or, a little bit faster, we can definitely account to that. We just need to know what that final speed is.
Okay.
Just as you're going forward. You don't have to know that now. Just keep that in mind going forward.
All right.
Awesome. And then I keep making you guys go back and forth, but you had just mentioned your height. 5.1 was close. You're kind of concerned about that. I can ease some concern there. That'll be completely fine. If you're right at 5.1 inches in height with that ring on the top, that's completely fine. I'm not worried about that at all.
Okay. That's good to hear.
And then kind of a larger item on slide 35, you do have high voltage on board, and you didn't call that out in your user guide compliance. It's that 50 to 100 volt system for the Langmuir probe. We definitely want to start tracking that. You can have it. We just need to be aware of it.
Yeah.
Okay.
It was a little confusing because that is going to be on Scout, which goes out. Yeah. It wouldn't necessarily be 50 volts on the payload. I mean, like on the Carol system itself. But we'll make a note of that.
Yeah, and that's potentially something that can be clarified in the user guide for sure. But basically, anything that goes up on the vehicle, has the potential of making a high voltage. We just need to track it.
Okay, perfect. Okay.
But yeah, that's not an overly worrying voltage. I mean, Rock-On's flying 500 volts, so not a problem at all. You just want to make sure to go ahead and update your user guide compliance. But yeah, no, overall, great job, everyone. I have a really good idea of your experiment. It looks like the deployment's not going to run into any of the longerons, which is a bonus. And your deployment system seems really robust. Just a couple design changes that you're mulling through as far as how to keep that ring gear locked in place. And then it really looks like you have a solid design here. So just kudos to the whole team for all the long hours so far. A lot of hours to go to build everything now, but at least we're to this point. Let's see here. Just looking through to make sure I didn't miss anything. All right. Cool. All right. So yeah, no, I think that was all my questions. Just the few action items. I will just go over just a quick summary here. It's just obviously that schedule, which I think you had as your timeline. Essentially, that's all we're looking for. Just upload that and keep that updated in your drive. I didn't grab what slide that was on, but
you're talking about the RockSat timed events, right? That deliverable?
No, slide 50.
The timeline.
Your detailed schedule.
Okay, perfect. Yeah, we'll upload that.
Yeah, that's perfect. This is actually a great example for other teams that are trying to figure out how to best visually represent, I guess, what's going on. But yeah, no, this is how your team is planning to meet certain deadlines and certain goals as we go through the process, and it illustrates very beautifully how you're going to meet these deadlines for each review and then each testing cycle as well. So another shout out to that there. But yeah, no, if you just put that in the drive, that would be excellent.
Okay, no problem. You got that.
And then we already talked about the high voltage. That's pretty much it there. And then, yeah, whenever you can, just that drawing of Nebraska's plate that they need to conform to. I think for that, if this dimension needs to change for this plate, definitely reach out to us and let us know, but we'll have Nebraska designed to this spec and you will you'll have to just keep an eye to make sure that if you need to shrink it a little more, that's your prerogative, I would say. So you have the ability to do that, or reshape it or move it where you think it fits. We just need to make sure to coordinate between the two teams. It's a little bit more difficult juggling two teams to keep them separate still, but kind of informed as to what's going on.
Is it possible for us to actually communicate with Nebraska, or?
Yeah, once we get past the CDR phase and closer to the STR phase, we have the team start coordinating definitely on the integration portion. But these design phases, we intentionally keep them a little separated so you don't start bleeding projects into each other's reviews. Your project is your project, and we don't want you worrying about their project unnecessarily, if that makes sense.
Yeah.
Basically, all brain power should be on your project. Cool. Alrighty. Great work, everyone. Before we go, I definitely would love to schedule your STR, which is going to be February 9th to the 13th. And if we keep the same day of the week and same time, that would put you at February 12th, 2026. Can't believe I'm already saying 2026. And then at 4:30 p.m. Mountain Standard Time. Does that sound like it would work for you all?
You guys think Friday?
I think
Yeah,
I don't
Friday.
class Friday. Friday would be great.
Yeah, Friday.
Not class.
Is that Friday? Is that Friday or Wednesday?
That would be a Thursday.
The 12th is a Thursday.
Can we do the 13th?
Oh, sorry. Yeah, you would be the 13th. Yeah, I don't know
No,
why you got
13th.
scheduled on the 12th.
13th Friday. Yeah, that works for me.
Okay, so the 13th at 4:30.
Good luck.
All right. Cool. So just confirming Friday the 13th at 4:30 Mountain Standard Time.
Sounds good.
Awesome. That is yours. And then if that needs to change, after you know your next semester's classes, just let us know, and we are happy to make any accommodations. But again, thank you for kind of hosting the space for Nebraska, giving them the opportunity to fly, and all the work that entails, modeling, getting them fit in there. Also, great work on everything that you've built up so far, and designed and built up so far. And I wish you all luck on the building and design tweaks coming forward.
Thank you very much.
Thank you.
All righty. Have a great one.
Have a good night.
You as well.
To you.
Great, thank you. See you. Good job.
Yeah.